All right, hello everybody, and welcome to the summary and review presentation for Chapter 1 of the Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller, and I'll be the instructor for this lesson. In this lesson, there were a couple terms that we defined and we introduced. We're going to go through them really quick. We talked about stability, the tendency of a vessel to right itself when it's in a liquid. MGB, metacenter, center of gravity, center of buoyancy. GZ, which is the righting arm. RM, or the righting moment. The stability triangle, which we'll get to in a second. GM, the metacentric height, which is the distance from G to M, upward being positive. And then stable, neutral, and unstable equilibrium, which is that case 1, 2, and 3 we looked at in the last lesson. Okay. So the first thing we talked about is that acronym, stability makes good boats. And what does that mean? As long as you have from top down the metacenter, center of gravity, center of buoyancy, then you have a ship that is going to be in stable equilibrium and it's going to be able to right itself safely. If you have M and G switched, then you're going to be in unstable equilibrium. Doesn't mean you're going to capsize. However, it does mean you are going to assume an angle of lull. Second note was the force of gravity equals the force of buoyancy, which equals the displacement of the ship. And we're going to be using this constantly throughout the rest of this entire video series. Now this diagram here is just showing that the center of buoyancy, as we incline a ship through small angles, I keep saying it over and over because it's very important that you remember 0 to 7 or 0 to 10, that the center of buoyancy swings through an arc. That arc has a radius BM, the center of which being the metacenter. Then we looked at the stability triangle. We have the center of buoyancy that originally is down here and it swings through that arc that we mentioned here to B1. Here's the center line of the ship. And as long as the center of gravity is along the center line of the ship, we can look at the stability triangle and look at how, if we change the center of gravity, how is our righting arm going to change? If our displacement stays the same, then it's going to change directly our righting moment, which means we're either going to be righted quicker or slower. Then from the stability triangle, we saw, okay, this is cool as long as G is down here. What if G is at M, or even worse, what if it's above M? Then we looked at in the last video, we saw case 1, where we have stable equilibrium, G being below M. Then we have neutral stability, or neutral equilibrium, where G is precisely at M. Then we have case 3, which is where G is above M, which is what's causing an upsetting moment that's going to be pushing the boat over. So those are all the topics that we went through. We're going to go through some example problems really quick just to show a few of these concepts in action. All right, so let's start off with a math problem real quick. So to start with number 1, here's the prompt for the question. All right, so as the prompt said, let's write down all the information. We have a vessel with a KM, so from keel to the metacenter, 21.5 feet. KG, keel to the center of gravity, of 18 feet. We displace 500 long tons, and we have a metacentric radius, that's that B, center of buoyancy to the metacenter, equals 13 feet. First, we got to find if it's stable or unstable. And then we have to find out how much weight would we add to 22 feet. So if we add weight to 22 feet high, how much weight would get our GM to equal 0, or to move that KG up if we're already stable, to move it up? Or if it's too high, would we be able to add weight to 22 to drop it down? Similarly, let's do the same thing, but for 31. And let's kind of comment on the difference between them. So let's start with the stable or unstable question. Step 1, what we have to do is we have to draw a diagram. We have to actually be able to see what we're working with. So we're going to assume that we're stable at first. Okay? So we're going to do make good boats. So good stability makes good boats. Top down, metacenter, center of gravity, center of buoyancy. Then the keel is all the way at the bottom. The first piece of information we have is from keel to metacenter is 21.5 feet. So K to M, 21.5 feet, right here. Next we have KG is 18 feet. So you go from keel to G is 18 feet. We know displacement is 500 long tons. Then we know BM is 13 feet. So from B up to M is 13 feet. All right, we drew a diagram with all the information we have. Step 2 is we got to find GM. If GM is positive, so G is lower than M, then we're stable. If it's above m, then we're unstable. So let's take a look at this. We have some extraneous information here, which means that in the prompt, there was some information that we don't really need in order to solve this. We know what Km is, and we know what Kg is. We're trying to find Gm, so Gm is just Km minus Kg. Simple enough. We know Km is 21.5, and we know that Kg is 18, right? So that means that Gm is just 21.5 minus 18, which is 3.5. That's a positive value, which means that we are stable. If we had a Kg of, say, 22, we would do Km minus Kg, which would be 21.5 minus 22. That would give us negative 0.5, which means we would be unstable. However, in this example, we are stable. So we have proper stability, making good boats. So here we would be stable. Now let's go into the second part of the problem, where we're asking how much weight can we add at 22 feet to get to neutral stability? If we add anything more than that, because we know that G is now at 18 feet and our metacenter is at 21.5 feet. If we assume that metacenter stays the same, so it's always going to stay at that 21.5, how much will get us to precisely neutral stability, knowing that anything more than that will get us unstable? Then let's do the same thing, but find out for Kg equals, we're placing the weight at 31. So the Kg of the weight would be at 31. Well, how much weight would get us there to neutral stability? So let's start with 22. We have to calculate the center of gravity, and we're basically saying instead of calculating the coordinate, we know what the coordinate is, we know where we're putting it, we know how much the ship displaces, we know the Kg of the ship. There's only one thing we don't know, and that's how much weight we have to put onto the ship in order to get a total Kg of the ship to equal 21.5. So basically to move it up 3.5 feet. So we go back into the equation, and you can go back to chapter 0 on the center of gravity, and you can look at that equation again. But it's basically R equals 1 over big M times the summation of little m times little r. So we have our little m, 500 times 18. We displace 500 long tons, and we have a Kg of 18 here. Then we're also adding an unknown amount of weight, 22 feet high. Then we're dividing by the total mass of the system, which is going to be 500 plus x, x being that unknown amount of weight. And we're going to eventually end up with a center of gravity of the entire system to equal 21.5, because that is what's going to get us a GM of 0, or to place that center of gravity up at that metacenter. So doing some very basic algebra, bringing the 500 plus x over, and then expanding these two parentheses, we have 10,750 plus 21.5x equals 9,000 plus 22x. Bringing this x over, bringing this 9,000 over, you'll solve for x, and x equals 3,500 long tons. That means with a ship with a center of gravity at 18, if we add 3,500 long tons, a position 22 feet above the keel, that is going to make that center of gravity come up to where the metacenter is. Okay, cool. That's a lot of weight to put there. Now, what if we put this weight, from 22 to 31? So we're only putting it 9 feet higher. How much less weight? Intuitively, you can think, okay, we're going to need less weight because we're putting it further away. It's going to be more of a moment causing the center of gravity to move. How much less is that going to be? So we said it the same way: 500 times 18, ship's displacement times the ship's kg, plus x times 31. X being the unknown amount of weight, 31 being the position that we're placing it at, divided by the total mass of the system, which is going to be 500 plus x. Bringing the denominator over and then solving for x, we get that same thing, 10,750 plus 21.5x equals 9,000 plus, now it's 31x. If you solve for x now, you have x equals 184.2 long tons. Okay? Now let's comment on this answer. At 22.5 and at 22 feet, we have 3,500 long tons. 31 feet, we only need 184 long tons to achieve neutral stability. To achieve neutral stability. That's right around 5%, maybe, about 5% of what we needed at 22 just to achieve neutral stability. Anything above 184.2, so 184.2, 001 or whatever, is going to get us right into unstable equilibrium, which means our G is going to be a little tiny bit higher than M, so we're going to assume an angle of lull. This is a very good reference example because on many ships, you'll have some sort of large deck. It might not necessarily be the fantail. It might be something like a flight deck or some sort of auxiliary deck. And many vessels have a center of gravity that's designed to be right around where the waterline is. So if you have a deck that's really high, you can see the higher you go, the amount of weight that you need to get your center of gravity up to where that metacenter is and then dangerously into unstable equilibrium just starts to fall off precipitously as you go higher and higher. So always be mindful of where you're putting weight on your vessel and how is that affecting the center of gravity. Obviously, if you have a heavier vessel, your center of gravity is going to shift slower and slower. If you have a lighter vessel, center of gravity is going to shift faster and faster. And you can do that on your own. You can set up the same problem, but let's just say your ship displaces 200 long tons instead of 500. Let's say it displaces 5,000 instead of 500. How's the center of gravity going to change? Is it going to be as bad as this? Are you going to have right around 5% needed at 31 versus 22? Maybe is it going to be 50%? I'll leave that for you to figure out. All right, and so with that, we've taken a look in this last chapter about metacentric height. We've talked about stability, when you can be stable, equilibrium, neutral, and unstable curriculum. We've talked about stability triangle, and we kind of put a little bit more information and knowledge on what we learned about in chapter 0, where we learned how to calculate the center of gravity and center of buoyancy. Now we started taking a look at how that affects ships in general. In the next chapter, chapter 2, we're going to start looking at weight shifts, weight additions, and weight removals, how that affects the center of gravity, how it affects the stability triangle, how it affects your metacentric height, and how it affects stability overall. But that's going to be in the next chapter. I'm going to conclude this video by saying I'm Lieutenant Timothy Mueller, and I hope you have a great day.